Hi everyone, my name is Elliot McDonald, and today me and my fellow students will be giving a short introduction to ourselves, the ATOM project, and the AMPL pipeline, preceding tutorial videos that we've developed in order to help you learn how to utilize AMPL in your own drug development research. First, I'll introduce myself. I'm a senior at Purdue University studying chemical engineering and data science. What's most interesting to me about the AMPL pipeline is that I believe that artificial intelligence is a vastly powerful tool that current chemical industries don't typically leverage, and AMPL has the ability to change that. I'll be presenting tutorial 1 and 2 on data curation and splitting datasets.
Hi, my name is Caitlin Yang, and I'm also a senior at Purdue. I'm majoring in cell molecular and developmental biology, and I'm interested in pursuing research and work in bioinformatics. I was particularly interested in the AMPL project because I've conducted research performing an in vivo drug screen using an animal model, and I was interested in how such a process could be made more effective using computational methods and cheminformatics analysis. The tutorials I'll be presenting are tutorials 3 and 4 on training and applying a simple regression model.
Hi everyone, I'm Amanda Wolf, a junior at Purdue University majoring in biological engineering with a concentration in cellular engineering and a minor in biotech. My interest in AMPL comes from a desire to predict end behaviors better in genetic engineering and also expand our innovation in personalized medicine. My tutorials that I'll be presenting are Tutorial 5, Hyperparameter Optimization, and Tutorial 6, Comparing Your Models.
Hi everyone, my name is Joel. I'm a senior at Purdue University and I'm majoring in biological engineering. I'm interested in machine learning and global health, and this fits with AMPL's mission in making drug discovery more efficient and accessible. The tutorials I'll be presenting are Training and Production Model in Tutorial 7 and Visualizations of Model Performance in Tutorial 8.
ATOM stands for Accelerating Therapeutics for Opportunities in Medicine, and it is a public-private partnership aimed at optimizing drug development processes, specifically by utilizing machine learning model-based approaches with experimental support. This project started in 2018 and utilizes a shared collaboration space at Mission Bay, San Francisco. ATOM has successfully released its first open-source predictive modeling product and has completed the first test of molecular design workflow.
ATOM's work is interdisciplinary in nature, merging fields like chemistry, data science, statistics, pharmacy, and engineering. As such, ATOM has extensive partnerships with different companies and institutions across the private and public sector, and these collaborations help accelerate its research and broaden its capabilities in silico drug screening. Collaborations with other national laboratories like Argonne, Oak Ridge, and Brookhaven allow for exciting R&D opportunities and innovations, and partnerships with academic institutions, pharma and tech companies, and cancer centers allow drug discovery and design to be furthered across fields and sectors. Partnerships like with the Purdue Data Mine allow for students like us across different departments to learn about cheminformatics and machine learning and contribute to ATOM's work.
Overall, ATOM aims to make drug discovery more efficient. Current drug discovery follows a mostly linear, sequential, staged approach that balances cost and risk. This is relatively inefficient. ATOM wants to take that drug discovery pipeline, which ultimately takes several years to bring molecules forward from target to human clinical trials, and accelerate this process using computational models. The current pipeline looks like this. First, we have lead discovery, taking 1 to 1.5 years. This is usually done in a pharma company. We screen millions of functional molecules to inform our design of new drug molecules. Next, we have lead optimization. It takes the longest time to do this. We sequentially design, make, and test thousands of new molecules. Then, we have the preclinical stage. This takes 1.5 years. There are lengthy in vitro and in vivo experiments performed before compounds move to human clinical trials, so this is a very time-consuming process. And even after going through all these processes and reaching the human clinical trials stage, we can run into problems. For example, the drug could be very potent, but have toxic side effects on humans. ATOM then plans to transform the drug discovery process by using machine modeling to find effective molecules faster. We're analyzing chemical compound libraries and building data-driven algorithms from them to efficiently predict useful molecules earlier, minimize extraneous testing, and jump ahead in the process of drug innovation.
Here's the ATOM modeling pipeline, and this is where AMPL gets its name from. This pipeline consists of 5 main stages: data ingestion and curation, which makes sure there are clean and usable data stored in the data lake; featurization, where molecular and chemical properties are turned into inputs that machines can read; model training and tuning, which uses machine learning tools to understand datasets of interest, such as drug potency, safety, and other pharmacokinetic properties. These models are stored in the model zoo. Next comes prediction generation, where we use the trained models to make molecular property predictions. Finally comes visualization and analysis, which allows the results to be interpreted and is stored in the results database. This can then be integrated into drug discovery workflows. If you want to look further into AMPL, you can check out its GitHub, where the codebase, usage details, and written tutorials are available on its webpage.
Bye!